This is part 6 of section 3.4. I want to solve this logarithmic equation. Okay, these both have log base 4, which is good. And I want to either get a single logarithm equal to a number or have a log equal to a log. Now, if this were a 0 right here, then I could move this log over to here and I'd have two logarithms equal to each other. I could drop them. But because this is not a 0, I will never get a single log equal to another log just moving things around. So I'm going to apply the property that says if I have the same base and they are subtracted, I get to combine those using division. So what I have here is log base 4 of, and when I have a division, I can put the root over the top and the bottom. Technically, you would write the square root of x plus 3 over the square root of 2x minus 1. And then your next step would be to combine them into one radical. But there we go. Okay, so now I have a single logarithm equal to a number. I can switch to exponential form. So the 4 comes over here, and I have the square root of x plus 3 over 2x minus 1 is equal to 4 to the 1/4 power. Okay, now I can simplify this a little bit. Just coming over here to scratch paper, if I rewrite 4 as 2 squared, I have 2 squared to the 1/4. I multiply those exponents. I would have 2 to the 2/4. So that's the same thing as 2 to the 1/2 power. And remember that a 1/2 power is a square root. So I write that as the square root of 2. So now, basically I've simplified this, and I have the square root of x plus 3 over 2x minus 1 equal to the square root of 2. So here we have a radical equation. And what we always want to do with a radical equation is to get at least one of the radicals on one side by itself. And it turns out that when we move things around here, we ended up with a radical equal to a radical. And since this is a square root, I'm going to raise both sides to the second power. If they were cube roots, I'd raise to the third power. Fourth roots, raise them to the fourth power, so on. When you square a square root, you get what's underneath it. So I have x plus 3 over 2x minus 1, and this is equal to 2. Okay, now I have a rational equation. And what I'm going to do is I'm going to multiply both sides here by this denominator to end up with x plus 3 is equal to 2 times 2x minus 1. Distribute the 2 to get 4x minus 2. Subtract x, I get 3x, add 2 to get 5. And right now I have 5/3 is equal to x. Now we really do have to check this because we have several places where this could go wrong. We're not allowed to take a log of a negative number. So I would need to plug this in and make sure that I don't get a negative under either of these square roots, okay, once I plug in this number. Also, we are not allowed to take a square root of a negative number. So what's inside has to be greater than or equal to 0. So we are allowed to take the square root of 0. We are not allowed to take log of 0. So when I'm looking at the domain for this thing, knowing that I have to take care of the domains on both, x plus 3 has to be strictly greater than 0, and this has to be strictly greater than 0. Okay. And then one more spot is that this is a denominator. So I would have to make sure that this never equals 0 either. Now it turns out that I can take care of all of these at once, because if this equals 0, then I'm not allowed to take log of the square root of 0 anyway. So I need this number to work out on both of these. Now, if I have 5/3 plus 3, I'd be taking the square root of 14/3. That's a positive number. It's okay. And then 2 times 5/3 minus 1 also gives me a positive number. So it is in the domain, and 5/3 is the solution to this equation. Okay, so what we've done already when we've talked about exponential equations, we've talked about exponential growth. And we talked about things like a bacterial colony. And in theory, they can replicate and grow, and they just keep growing without bound. And that's in theory. That is assuming that you have infinite space, infinite fuel, infinite oxygen, everything that these bacteria could possibly need in order to thrive. Now, that's just not realistic, okay? And so it usually turns out that there's some reasonable upper bound of possibilities. After a certain point, you're not going to have the resources to keep things growing. And in the 1830s, this Belgian mathematician, Verhulst, added another constraint on growth, basically saying there is a limited, sustainable maximum population of a species that the habitat can support. At a certain point, you're going to run out of food and water and oxygen, all that kind of stuff. And then he used that to create what we call the exponential or the logistic growth model. So logistically, realistically, how fast can this thing grow? Okay. M is the largest value it could possibly be. It's called the carrying capacity. So whatever your numerator here is, that is as big as this thing can possibly get. Okay. K is the rate of growth, which is going to be a percentage. We'll write it as a decimal. A is some positive constant. If we have all of that, then the population at time t is given by this formula. Okay. On some of the problems, you will be given your logistic growth model with your M, your A, and your K already in it. You'll be asked to use it and just do some calculations. On other problems, you're going to be given enough information, and you're going to be asked to find A and K and M and use that to create your model, in which case you're going to be able to use it again. So in our example problem, I'm going to do a version of the harder one, just so you have everything you can possibly need to get these problems worked.